This part is the demonstration of using SAS to run the code for lecture number 9. Right. So first step is always what we need to set up a library. So my library is called lecture number 9. And then because here I'm using a desktop version of SAS, so I don't have to worry about the way to specify the directory when I'm using eLabs. But if you use eLabs, you can again follow this format to load the your directory and set up that as your library. All right. So the first part is I create a new data set. It's not a new data set, but just add a new variable to the data set called the LAC2 systolic blood pressure data. And then here I create a new variable, which is age squared. So I called age2 equal to age times age. And then, so here's a little bit typo right here. I think I have to be LAC number 2 SPV. So this is exactly the same data as we show in lecture number 2. All right, so after we run this part, you can see there's no new more data set added to the library. Instead of add new data set, we actually create a new variable called age2 into the data set called LAC2 SPV. And then the next step is to run the regression model and to check the influential point. Again, here it's a little bit typo right here. Just reverse the E and the C right here. Okay, so after we run that, so we see this SAS output to check if every single observation is an influential point. So here what we identified is the observation number 2 with a systolic blood pressure equal to 220 is a influential point because when we check the student, our student or the jackknife value, so this value is way above the critical value threshold as 2.06. Right. And next one, we actually create a new data set called clean. And this is a data set that remove the outliers with influential point observation number 2 with systolic blood pressure equal to 220. So the way to do that is we set the previous data set LAC2 SPV data and then remove the record if SPV equal to 220 because we know the value for the dependent variable. So we can use that, or the other way is you can remove it based on the observation number. But here, this is the easier way because we know 220 is an outlier. Okay, run this. Okay, so the way I create a new data set called clean because I didn't specify the library name. And then is automatically saved to the work library, which you can find from the work. So if you click on the Explorer, and you have a library which store the original data set like to SPV, and the clean data set is saved into the work data set, the work library. So this is a new data set. So here we have a total number of 29 observations because we removed the previous record number 2. So you can see there's no individual number 2 in this data set because that's an outlier. All right, and next one, so if you still remember, we did a check of the correlation between the linear term of age and a quadratic term of age using the PROC correlation. So that's the PROC CORR. Once we run this, we got this matrix of Pearson correlation coefficients. We got the 0.98, which is highly significant correlation between the age and age quadratic. And then we run a regression model with both age and age squared as a predictor, and we check the variation inflation factor VIF. And you see we have a VIF equal to 31.8, which is way off the benchmark, which is 10. All right, and the next one, we create a new variable, which is the centralized age. We call age center. This is by subtracting the mean value, 45.07 for each observations. And then create a quadratic form we call age center 2. And here I didn't create a new data, I still use the same data set, the clean data set, but we just add 2 new variables on top of the current variables. Okay, and then we can go back to Explorer and we check the clean data set, and there's 2 new variables being created. Age center, which is the centralized age linear term, and the age center 2 is the centralized age squared, which is the quadratic term. Okay, and then we check the correlation coefficient between the centralized age and the centralized age squared. And you see we got a correlation coefficient equal to -0.21 and the p-value about 0.27, which is not significant. And then in the next one, we run a regression model to recheck the variation inflation factor. Now the VIF equal to 0.04, which is less than 10 or less than 5 as benchmark. Right, and then we need to decide the final model, because in the previous model, we see that the quadratic term of centralized age is not statistically significant. So it's no matter we do a t-test or we do an f-test, we will got the same p-value. And then in the final model, we should remove the quadratic terms, and then which means we can only include the linear terms of age. So as I said, it doesn't matter. We can include either the original age measurements, or we can also include the centralized age. There's no difference, but the parameter interpretation will be a little bit different. And this is going to be the final model with a beta 0 equal to 97.07 and beta 1 for age equal to 0.94. And you see both terms, beta 0 and beta 1, are statistically different from 0. Okay, in the next one, which is also the last one, is the test, the lack of fit for higher order polynomials. Okay, and the key result is this first table called analysis of variance table. And then the test for model with 1 degree of freedom is for the reduced model that only included the linear term of age centered. And this one got a highly significant value, and this is the sum of square being explained by the linear term of age, because that's only a predictor variable in this model. And then the next part is the partition of the error terms. So error terms will have a degree of freedom equal to the total number of degree of freedom, corrected total minus the model degree of freedom, which is 28 minus 1 equal to 27. And this 28 is equal to sample size n minus 1. So n is 29, 29 minus 1 is 28. And then this two part actually is the further partition of the error terms. So the lack of fit here, the sum of square is the sum of square explained by the higher order polynomials from the quadratic term to cubic term all the way to x to the power 23. So that 22 terms explain a total number of about 2090 sum of squares. And this is not statistically significant because we got a p-value equal to 0.4394. And that fail to reject the null hypothesis that these 22 terms is not equal to 0, at least one of 22 terms with a beta not equal to 0. And therefore, adding the higher order polynomials from the quadratic term all the way to the power 23 is not necessary, because it would not statistically significantly add to the prediction power of the model. All right, and then this will be the final model using the linear term as the centered age. Then if you want to compare this with the final model we use here, you can see we get exactly the same beta value, beta 0 and beta 1, and also the p-value are the same. So this really doesn't matter if you only have one terms there. With a linear term, it really doesn't matter if you use original age or you use the centralized age, which is the age minus the mean value of age. Okay, and this is the SAS demonstration for lecture number 9.